Hey guys, welcome back. I am going to try and finish up the Chapter 5 handouts. I'm starting on page, I think it's page 29. This last problem that we were doing yesterday that we did not have time to finish. So number 4, using the sample data from this table, which has a total of 100 people. So question A, if one of the 100 subjects is randomly selected, find the probability of getting someone who told the truth or had the polygraph test indicate that the truth was being told. So there's only one selection being made here. There's no multiplying that needs to go on. This is just a basically A or B question. So someone who actually told the truth, that would be these people. Subject actually told the truth. That's this row. Or had the polygraph test indicate that the truth was being told. Polygraph indicated truth. That's this column. That's these people. So the point here is notice that there is overlap, and as always, you don't want to double count the overlap. So the total number of people that we're talking about here would be the 3 plus the 65 plus the 15. Okay, that's the number of ways to get a person in one of those categories divided by total of 100 people is 0.83. Okay, so 0.83, that's the answer for A. All right, B, if 2 different subjects are randomly selected. Okay, so now we are making 2 sequential selections. We're going to have to do some multiplying. Find the probability that they both had the polygraph test indicate that a lie was being told. Polygraph indicated a lie are these people, and that is a total of 32. Okay, so I've got 100 people in the bag. The probability that I reach in and get one person where the polygraph indicated a lie, there's 32 ways for that to happen out of 100 total. And then I want 2 different people, which implies without replacement. So I got the first person, I'm going to set them aside. What's the probability that I get another? Well, now there's only 31 of them left in there, and there's only 99 total people left in the bag. So if you multiply all that out to 3 significant figures, I've got 0.100. And then part C is to repeat that, but this time assume replacement. So it starts exactly the same. Well, there's 32 ways for it to happen out of 100. But then whoever it was that I selected, I put them back in the bag. So when I go to pick the second person, there's still 32 ways, and there's still 100 people in the bag. So the result of that calculation, if you do it, should get 0.102. So again, that's a slight approximation, but again, the only difference is in the third significant figure. Oops. All right, let me go on. Sorry, I've got this brand new other tool that I downloaded, which is allowing me to write on the screen, which actually I'm finding pretty handy so far. All right, the birthday problem. And you know what? I was going to skip this today anyway. Unfortunately, it's one of my favorite problems to work through with the class because it's fun, it's interesting. We're already short on time, and I literally can't do it right now anyway because I need all of you with me. But let me just kind of briefly summarize that the problem is to find the probability that at least 2 people in a group of people have the same birthday. So what I typically do is, and what I would have done if we had had time to do this, is say, okay, there's 29 students left in my class, plus me, so we have a total of 30 people. What is the probability out of these random 30 people that at least 2 of us have the same birthday? Just month and day, the year doesn't matter, okay? And the assumptions that go into this calculation are assuming only 365 possible birthdays. Technically, there's 366. Assuming that any day of the year is equally likely to be born on, and assuming that there's no twins in the class. I had to add that because I have had twins in the past. Okay, so like I say, I usually step through it step by step. It takes quite a while. I am going to just cut right to the chase and tell you. So again, there's 30 people in the room. Guess. Pause this for a minute before I tell you the answer, and guess. What do you think the probability is that at least 2 of us have the same birthday? What do you think? At least 2 of us born on the same month and day. All right, so, sorry, I had to pause and think about it too myself. The answer is, and typically, people would guess a pretty low probability. 1%, 5%. A pretty low probability that 2 of us would have the same birthday. In fact, for 30 people, the probability that at least 2 people have the same birthday is about 71%. So in fact, if we were all there today, and if we all went around the room and said our birthdays out loud, there is a 70% chance that at least 2 of us would have the same birthday. Okay? So again, I don't have the time or the opportunity to go through all the detailed steps of the calculation. So if you're, if you want, you can Google it. It's a very well-known problem. You can do some simulations online or whatever. Now, on this page 33, I will come back to this because I kind of use the birthday problem as a way to introduce how to do permutations on your calculator. Because in this next section that I'm going to do right now, we are going to do permutations and combinations. So get your scientific calculator out, because a big part of this is learning how to do it on your calculator. So normally I would do this here. What I'm going to do is I'm going to go on and then I'll come back. These are the specific commands for various types of calculators, okay? So what I'm going to do right now is just go on and introduce the topic. Sorry, I'm just getting my notes out. So this is the last section here in chapter 5. It's all about counting techniques, and the whole principle of counting means finding out how many different outcomes an event can have. For example, and this was a year ago, this was a Powerball drawing, and it had this crazy record prize, $1.6 billion grand prize. So the question that at the end of the section we will be able to answer is, if you buy a Powerball ticket, what is the probability that you will have the winning numbers? The only way to calculate that probability is to know how many ways are there to choose the numbers. Okay? So the way they do the Powerball is they draw 5 different white balls out of a drum that has 69 different white balls in it. And then they draw 1 red ball that has 26. Okay? And you don't have to pick the white ones in the right order, you just have to have the right numbers. So again, how many different outcomes are possible? What's the probability of winning? And again, at the end of the section, we will calculate that. And really, that is the whole purpose of using counting methods, is to find out how many different outcomes there are for a particular event happening. Okay. We've already looked at a lot. How many outcomes when you roll a single die? There's 6. How many when you roll 2 dice? There's 36. When you draw a single card, there's 52. When you toss 2 coins, there's 4. For a couple having 3 children, as far as the gender sequences, there's 8. We drew a tree diagram of that. Okay. So we're going to look at more complex situations. All of those that we've already looked at are pretty simple to just kind of figure out. We're going to look at much more complex situations and figure out how to count the total number of possible outcomes. So the techniques to count, first of all, just list the outcomes. And basically, everything that we've done so far is that, just listing them out. Okay? But what we're going to do in this section is we're going to learn 3 new methods. Okay, so first of all, we are going to learn something called the multiplication rule. I'm not going to write it all out. We're going to learn about permutations. And finally, we're going to learn about combinations. All right, so all 4 of these are valid techniques to use for counting. All right, so let's start with the multiplication rule, also frequently called the basic counting rule. So in this case, it's very similar to what we already learned for the multiplication rule for probabilities. We're basically talking about sequential trials or sequential events. So like we're going to pick something from a first category and then pick something from the second category and so on. And each event from each category can have a certain number of outcomes. So for example, whatever the first category or event is, maybe it has P, total outcomes. Maybe the second category, B, has Q, outcomes. And maybe the third category has R, outcomes, and so on, however many you have. And then the multiplication rule says that to find the total number of possible outcomes, multiply together the individual number of outcomes for each category. So in other words, your total number of outcomes would be P times Q times R times however many more. So for example, some things we looked at before, number of outcomes when you flip 2 coins, we drew a tree diagram. We already know it's 4, but we could say when I flip the first coin, there's 2 outcomes, times when I flip the second coin, there's 2 outcomes. Okay, so I multiply them, there's a total of 4 outcomes. Rolling 2 dice. We already know there's 36 outcomes because we looked at the two-way table. But you could say, well, when I roll the first die, there's 6 outcomes, times when I roll the second die, there's 6 outcomes. 36 total ways, 36 total outcomes. Or a couple having 3 kids. The first, there's 2 outcomes, boy or girl, times the second, boy or girl, times the third, boy or girl. Okay? It equals 8. So all of these we already knew from other methods, but it can be a lot easier to just use this, idea of counting to multiply them together instead of listing them all out. All right, so for example, assume that a license plate consists of 4 letters followed by 3 digits. How many plates are possible, assuming that the letters and digits may be repeated? So your events are, well, I got to pick my first letter. How many outcomes? There's 26 letters in the alphabet, so obviously it's 26. I'm going to pick the second letter, keeping in mind that we can repeat letters. So there's still 26 outcomes. Third letter, still 26. Fourth letter, 26. Pick the first digit. How many digits are there? And the answer is not 9 because you have to include 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are actually 10 digits. Pick the second digit, I can repeat. Pick the third digit, I can repeat. Okay? So the total number of outcomes, I just need to multiply all these together. So 26 times 26 times 26 times 26 times 10 times 10 times 10. All right, I'm kind of losing my way as far as drawing a straight line here. All right, if you multiply all those together, you should get 4, 5, 6, comma, 976, comma, 0, 0, 0. Okay. So in other words, there's a lot of ways. And just so you know, when we're doing this kind of a method, this is what I refer to as the fill in the blank method. So in other words, I would say, okay, my first letter, second letter, third letter, fourth letter, first digit, second digit, third digit. So I just kind of have all those blank, and then I would be like, what number do I need to fill in each case, knowing that I'm going to multiply them all together. So this is very typical with problems like this, with passwords, or combination locks, or social security numbers. If you have a certain number of, blanks that need to be filled in, just go ahead and draw those blanks and then fill them in with the total number of possibilities. Okay, so now as far as applying the counting rules to actually calculating probabilities, what is the probability of randomly generating the 4 letters followed by 3 digits and having it be your license plate? Okay, so basically we want to go back to our basic definition of probabilities, which is in the numerator, I'm not going to write this out, the number of ways it can occur, over in the denominator the total number of outcomes. Okay. So in this case, the number of ways that it can be your plate is only 1, over the total number of outcomes is this number. Okay. So 1 over that, if you divide it out, it's 0. Followed by 8 zeros. 0.0000000219. Okay? And I meant to write that here. Sorry. One more question. How many plates are possible if the letters and digits may not be repeated? In other words, without replacement. Okay, so in this case, again, if we use the fill in the blank method, we've got letter, 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 digit, 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 and then knowing that we're going to multiply all of these together. So how many ways to pick the first letter? Well, there's 26. But then whatever letter that was, I can't use it again. So how many ways to pick the second letter? There's only 25. And then I can't use that one again. So 24 and 23. And the same with the digits. 10 digits for the first one, but then I don't replace that one, so there's only 9 ways to pick the second and 8 ways to pick the third. Okay, so in this case, if you multiply them all out, I will just say this instead of writing it. It's 258, comma, 336, comma, 000 possible plates. All right, let me go on to the next page. And before we get into permutations or combinations, we have to discuss factorial notation. So this is just a mathematical notation. It is written like this, n exclamation point. That is how you write factorial notation, and you actually say it as n factorial. So what it means is n factorial equals n times n minus 1 times n minus 2 times, and so on, all the way down to, say, times 3 times 2 times 1. Okay? And notice that n has to be a non-negative integer. So the definition may not totally make sense, so let me give you a few examples. For example, 4 factorial means 4 times 3 times 2 times 1, which if you multiply all those is 24. Or 8 factorial means 8 times 7 times, and so on, times 6 times 5 times 4 times 3 times 2 times 1, and if you multiply all those together, it's 40,320. And also just a comment that by definition, 0 factorial, although it may not seem to make sense, is equal to 1. Again, by definition. And just an additional note that you do have a factorial function on your scientific calculator. So why don't you pause for a minute and try to find it, and then try to, say, reproduce either or both of these numbers. So what you should be looking for is a button that is maybe like this. And it's probably not a main function, it's maybe a second or third function. For some of you that have certain TI models, you may have to go into a menu that may be, so your button may be either labeled prob or stat. And if you hit one of those buttons, then it should take you to a screen where it gives you 3 options. And one of them will be with a P, one of them will be with a C, and one of them will be with an exclamation point. So this would be permutations, combinations. This is what we're talking about right now, factorial. So you probably need to enter the number first. So for example, enter the number 8 and then go into the menu and select the exclamation point and then hit, I don't know, whatever you got on your calculator. If it's just equals or enter, or I'm not sure. I don't have all the different calculators. So pause for a minute, make sure that you can find how to do that on your calculator. Make sure that you can reproduce these numbers. Okay? All right, so I will go ahead now and talk about permutations. So a permutation, just the definition, is any different arrangement or sequence or ordering of a certain number of objects, whatever the objects are. So again, arrangement or sequence or ordering, all three of those are kind of key words. And basically the key point here is that order matters when you are counting up permutations. The whole idea behind permutations is how many different ways can I arrange these objects in a specific order. So for example, let's say I have a group of 3 letters, A, B, and C. And then the question is, how many different ways can I arrange those 3 objects? All right, well, let's just list them. So we can start with ABC. I can keep the A and then switch these, so I'll have ACB. All right, so now let's put the B first, and then I would have A and C. I can keep the B here and then do CA. Or I could put the C first and have AB, or I could do C, B, A. Okay. And that's it. There's no other way to arrange these 3 objects. So in other words, there are 6 different permutations of these 3 objects. Okay? 6 permutations of the 3 objects. So now for a slightly different example, let me go to the next page. This time, let's say we have 4 objects, 4 letters, A, B, C, and D. So last time I arranged all of them. This time I am just going to select 2 of them at a time and arrange them. So how many different ways can I do that? Well, let's do this again by listing, and we'll do it in a very methodical manner. So let's start by doing the first 2, A and B. All right, but then if I switch them, that's a different permutation, so B and A. Okay. And then let's stick with having A, so let's do A and C. And then let's swap the order again, C, A. And then still with A, I can do A with D, swap the order, and I would have D and A. All right, so I've got A with everybody. So now let's start with B. So let's do B and C, swap the order. So I've got C with B. Let's do B with D, and then swap the order. So I've got D and B. So I've got everything with B now. So now let's move on to C and D. Switch the order, and I've got D and C. And again, there's nothing more that we can do. That is all the different ways I can take two of the letters at a time and arrange them in a particular order. So in this case, I would say that there are 12 permutations, okay, of 4 objects taken 2 at a time. Okay. So as you can see, it can get a little tedious to list out all the different permutations, especially as the numbers get bigger. For example, if I had 6 objects, and if I took 4 at a time, how many permutations of that would there be? And I can tell you that you would not want to list them because there are actually 360 permutations of 6 objects taken 4 at a time. So this is why we don't want to have to list them, and this is why we have a permutation rule, a formula that tells us how many different permutations there are, how many different ways to list them in a particular order. So here is the formula. NPR is equal to n factorial divided by quantity n minus r factorial. So n is the total number of objects that you have. R is how many of them are you selecting at a time. And you would read this as the number of permutations of n objects taken r at a time. So for example, what I just did on this page was I had 4 objects, the letters A, B, C, D. I selected 2 of them at a time. So if we use this formula, 4p2, okay, then I would have 4 factorial, because that was n, the total number of objects, over 4 minus 2 factorial. Okay. So in 4 factorial is 24. This quantity, 4 minus 2, is 2. 2 factorial is just 2 times 1, which is 2. Okay. So this quantity is 12. And we just saw that because we just listed 12 different permutations. Okay. Or from the previous page, I had 3 letters, ABC, and we listed the permutations of all 3 of them. We saw that there were 6 of them. So that is equivalent to doing 3 permutation 3. In other words, 3 factorial over 3 minus 3 factorial. 3 factorial means 3 times 2 times 1, which is 6. 3 minus 3 quantity is 0. 0 factorial is 1. So this equals 6. Excuse me. And we already saw that on the previous page, that there were 6 ways to do that. Okay, and then just a comment on that last example, this one, is that this is an example of the special permutations rule. Okay, this is when we have a certain number of items, n of them, and we want to arrange all of them. So in that case, I had 3 letters, A, B, and C, and I wanted to see how many ways to arrange all 3 of them. Okay, so a general rule then for permutations for n items is that you can arrange them in order n factorial ways. Okay, so for this specific example on the previous page, the letters A, B, and C, there were 3 letters. So in other words, it's saying we can arrange them in 3 factorial ways, which would mean 3 times 2 times 1, which is 6. Okay. And then just a comment that when you say n factorial, that is the equivalent to saying n items permutation n ways. Okay, so you've got n items and you're arranging all of them. All right, so this now is a perfect place for you to go back to the previous page. Let me work my way back there, sorry. All the way back here, page 33. Okay, because what I want you guys to all do right now is stop and make sure that you can do the permutations, and also while you're at it, figure out the combinations on your scientific calculator. This is a key thing. I just showed you the formula for how to calculate the number of permutations. I do not actually want you to use that formula. I will get angry with you if I see you actually using that formula. And the reason is that formula is built into your calculator. It is a function on your calculator. And that is what you should be doing. Use your calculator to do the calculation for you. Okay, so if you have any of these particular calculators, then I've already shown you the commands here. And kind of ignore these numbers here. This was the specific calculation I was doing. And again, keep in mind, this is for NPR. Okay, so in this particular case, this was for the birthday calculation. N was 365, so that's why I have all these 365s here and so on. But just substitute whatever your total number of items is. And then for R, how many of them are you selecting at a time? Okay, so if you have one of these calculators, I've basically already gotten the commands written out for you here. I know a lot of people, I think maybe my list is a little outdated. I need to update it. Like I mentioned before, if you have a particular TI calculator, you may have to go into a button that either says prob or stat. And again, like I said, you will see options that include P, C, and exclamation point. And generally, you want to enter the number N first, the total number of objects, and then go into the menu, pick, do you want to do a permutation, a combination, or a factorial? And then, assuming you're doing one of these two, enter the second number, R, and then hit your equals button or your enter button or whatever. Okay. Let me give you a couple more easier test cases. 8P2 is equal to 56. So in other words, the permutation of 8 objects taken 2 at a time is 56. And then as long as we're learning how to do permutations, go ahead and find your combination button. It should be very close to the permutation button on your calculator, or like I said, if you have to go into the menu, it's right there. Okay, so 8C2 is equal to 28. Okay, so use these as your test cases. And really, I strongly urge you, pause this for a minute, figure out how to do that on your calculator. Hopefully your calculator is listed here, or you've got the menu item, and then like I said, go to one of these options. Try to figure out how to do it, okay? And if you still can't, if you're desperate, you can Google your specific calculator model instruction manual. There will be an instruction manual out there posted. I know, horror of horrors, but actually go look at the instruction manual and try to figure it out. Okay? So again, try to pause, figure out how to do this. If you absolutely can't figure out how to do it, that's fine. Let me know, hopefully tomorrow, if we're in class. I'll help you. Although, I probably don't have your exact calculator model, and often the best advice I can offer is talk to another student that has the same calculator and see if they have figured it out. Okay? But it is vitally important that you know how to do permutations and combinations on your calculator. Okay? All right, so pause if you want. I'm going to erase all this and go on. And I'm going on. Sorry, I'm trying to get back to where I was. All right, so we did this. Okay, permutations with non-distinct items. So in this case, non-distinct means I can't tell them apart. They look exactly the same. So, you know, above, we did an example with the letters A, B, C, and D, right? We didn't arrange all of them. We only chose 2 at a time. But if we were to arrange all 4 of these, how many different arrangements would there be? Well, in this case, n equals 4, there's 4 different objects, and we just went over the special permutation rule, how many ways to arrange, you know, 4 different objects would be 4 factorial, which is 4 times 3 times 2 times 1, which is 24. Okay. So that is the case where all the items are distinct. I can tell them apart. So now, let's say we still have 4 objects, but 2 of them are the same. So I have the letters A, B, C, and C. So C and C are the same. I can't tell them apart. So just first of all, what do you think? We just said A, B, C, D, 4 different objects. There's 24 ways to arrange them. Now we've got 4 objects, but 2 of them are indistinguishable. So what do you think? The number of ways to arrange these, is it going to be what? More? Less? What? What do you think? It's going to be less. Okay? These 2 are the same. We can't tell them apart. So it's going to be less. So let's go ahead and list them. So let's start, as always, trying to be methodical. Let's just start with A, B, C, and C. Let's see what next. We can do, if we keep the A in the front, then we'd have to do a C, B, and a C. And then still keeping the A in the front, we could do C, C, and B. And there's no other way to do it with A in front. All right, so let's switch. Let's go with B in front. So let's go B, A, C, and C. Okay, and then let's keep B in front. And let's do B, C, A, C. And then still keeping B in front, let's do B, C, C, A. All right, so there's no other ways to do it with B in front. So let's start again with C in front. So we could have C, A, B, C. We could have C, A, C, B. We could have C. Now let's put B here. B, A, C. Let's keep C here, of course. And B, C, A. C, okay, the only other thing we haven't done is C in the second position. And then we could have AB. And then C, C, B, A. Okay. So if we have 4 different objects like we did up here, there was 24 ways. So we still have 4 objects, but 2 of them are the same. And now there are only 12 ways, 12 permutations. Okay? And as you may suspect, there is a formula to deal with this special case. The special case being that one of the items or more is repeated. All right, so the formula for this, the number of permutations of n objects. So we have n1 of one kind, n2 of the second kind, and so on. All right, so the number of permutations will equal, so first of all, the total number of objects factorial, and then divided by how many of the first kind factorial, how many of the second kind factorial, and so on, all the way up to how many of the last kind factorial. Sorry, just trying to draw that dividing line all the way over. All right, so that may seem a little gibberish-ish. So let me show you an example to try to explain that. How many different 6-digit numerals can be written using these 6 digits? Okay, so there are 6 total numbers here. So in other words, n equals 6. Okay, so n equals 6, but we have some repeats. We have 4 repeated 2 times. We have 5 repeated 3 times. So therefore, the total number of ways, or the total number of permutations, is going to equal, so n factorial, which would be 6 factorial, because there's 6 numbers, divided by 2 factorial, because there's 2 4s, 3 factorial, because there's 3 5s, and then 1 factorial, which really we can disregard because that just equals 1, but that refers to the single 7. All right? So this should equal 60. And again, if you are doing this on your calculator, when you do the 6 factorial divided by, then make sure you put parens around your denominator. And make sure you can do that and get the correct number. Okay. All right, so let's go on to combinations. So combinations are different from permutations because the order of the objects does not matter. The order does not matter. We're not talking now about how many different arrangements. We're just talking about how many different groups. How many different ways can you group the items? I don't care what order they're in anymore. So for example, we looked at the letters A, B, C, and we looked at how many different ways we could order them. And we found that there were 6 different permutations of those 3 letters. How many different combinations of those objects are there? Kind of a trick question, really, if you think about it. Because I don't care what order they're in. I'm basically just throwing all 3 letters into a bag. There's only one different combination. Just the group of the letters, A, B, C. I don't care what order they are in. Okay? And another example, we looked at the group of letters A, B, C, D. And we found that there were 12 permutations when we were selecting 2 objects at a time from this group. So now let's ask a different question. How many combinations of 2 objects can be selected from that group? All right. Well, we listed them last time. Let's list them again. So let's start. So the first combination would be the letters A and B. Okay. And then last time, when we were listing the permutations, then we said B and A because that is a different ordering. But this time, we don't have to do that because I don't care about the order. I am only looking at the different groupings of the letters. So instead, I'm going to go on to A and C, and then A and D, because I don't care what order they are in. All right, so then we've got A with everyone. Let's go on to B and C, B and D. All right, now we've got B with everyone. So let's go on to C and D. Okay, so in this case, there are only 6 combinations of two objects versus 12 permutations. Okay? In general, there will be fewer combinations than permutations. All right? So, as before, with the permutations, there is a formula for combinations. So let's go on to that. So the combinations rule would be NCR equals n factorial over r factorial times the quantity n minus r factorial. Okay? So NCR is the total number of combinations. N is the total number of objects. R is how many of them are you taking at a time. And then you would literally say this as the number of combinations of n objects taken are at a time. So for example, find the number of combinations of 25 objects taken 8 at a time. So in other words, I want you to find 25 C8. And I don't want you to find it using the formula. I want you to find it using your combination function on your scientific calculator. So again, hopefully you have already figured out how to do this. So here is one more test case. So go ahead and try that. And you should find that it is 1,081, comma 575. All right. So again, it is critical that you can do this on your calculator. So please get your calculator out. Google the manual if you need to. Figure out how to do these calculations on your calculator. All right. All right, so kind of another sort of a special case when we are selecting from two or more subgroups. So in this case, I'm using an example where I've got a dozen eggs. 3 of them are cracked. So the problem is we are randomly going to select 5 of them, and we're going to hard boil them. And then the question is, how many outcomes are there for the following events? All right, problem A. Select any 5 of the eggs. Okay, so in this case, apparently, I don't care if they're cracked or not. I just want to grab 5 eggs to hard boil. So in this case, the total number that I am selecting from is 12, because there's 12 eggs. Okay, and we are going to choose R5. Okay, we're going to choose 5 of them. And clearly the order of the eggs doesn't matter, so it's just a combination. It's a combination of 12 items taken 5 at a time. Okay, so just do that on your calculator. How many different ways are there to do a combination of 12 objects chosen 5 at a time? All right. If you've done it on your calculator, you should find that the answer is 792. All right, so the second part of the question is, all of the cracked eggs are selected. All right, so in this case, we are now splitting the question up. There's kind of 2 subgroups, either the cracked eggs or the not cracked eggs. And we want to make a certain number of selections from each group. So in this case, we want to count the number of ways to select from each group and then multiply them together. All right? So in this case, we are going to use the combinations rule. Okay, to determine how many outcomes from each subgroup. And then we are going to use the multiplication rule to multiply the outcomes together. All right. So I am saying that I'm going to select all of the cracked eggs. Okay, there are 3 cracked eggs. So in other words, I'm going to select 3 of the 3 cracked eggs. How many ways can I pick all 3 of the 3 cracked eggs? Okay. Intuitively, we know there's only one way. You're picking all 3 of the cracked eggs. All right. So that makes sense. So there's 3 cracked eggs. I'm selecting 3. In other words, I'm doing 3 combination 3, which if you do that on your calculator, which you should, it is equal to 1. Okay. So I still need to choose 2 more eggs because I want 5 total. Okay. So what is left is a total of 9 not cracked eggs. Okay. That is all of these guys. So out of the not cracked eggs, I want to select 2 because I need to have a total of 5. That was stated in the problem. Okay. So how many ways can I select 2 of the not cracked eggs? Well, in other words, I want to do a combination of, there's a total of 9, but I want to select 2. Okay. So this, if you do it, 9C2 is 36. And let me come, yeah, I already did the previous one. 3C3 is 1. Okay. Oh, crap. So in other words, I've got sorry, we already did both of those calculations. 3C3, which is 1, times 9C2, which is 36. Or in other words, 36 total ways to select all of the cracked eggs. Okay. So then the probability that all of the cracked eggs are selected, well, we just calculated there's 36 ways to select all the cracked eggs over, and we already previously had calculated there's 792 total ways to select any of the 5 eggs. Okay. So if you divide that out, it should be 0.0455. All right, this is supposed to be a 0. It didn't look so good. Okay. All right, so let's go on to the next page, which has an example very similar to the one we just did. So in this case, what if we want to choose 1 cracked egg and 4 good eggs? Okay. How many ways are there to do that? Well, again, keeping in mind that there are a total of 3 cracked eggs, and we want to choose one of them, okay? So the number of ways to select that, so out of 3, I want to choose 1. And then not cracked eggs, so in other words, I want to choose 4 good eggs. So out of the 9, I want to choose 4. Okay, so again, I want to choose 1 cracked one, 4 cracked one. Crap, sorry. I want to choose 1 cracked one, 4 not cracked, for a total of 5. Okay. So in other words, 3C1 is 3 times 9C4 is 126. Okay. So the total is 378 ways to choose that particular grouping of eggs. Okay. All right, so let's get back to the Powerball example that I mentioned at the very start of the section. And the great news is, really, that now we have the methods to calculate how many possible outcomes there were for this Powerball drawing a year ago, okay, that had like $1.6 billion payout. So, how many different outcomes are there? How many different ways to choose the numbers? Draw 5 different white balls out of a drum that is numbered 1 through 69, okay? And then draw 1 red ball that is numbered 1 through 26, okay? So in other words, I want to choose 5 numbers out of these. So, and they don't have to be in order. So I just want to do a combination of 69 numbers, taken 5 at a time. And then here, I want to just choose 1 number out of 26. So that would just be a combination of 26 numbers, taken 1 at a time, and then we're going to end up multiplying those. So if you do C69, 5, you should get 11,238, comma 513, and then multiply that by, this should be just 26. Okay. All right. And so the final result is 292, comma 201, comma, 338. So in other words, that is the total number of ways to pick a Powerball ticket number. Okay, that many ways. So therefore, the probability that you win, there is only one way to win. Okay, so there's only one correct combination of numbers divided by this big giant number. Okay, so if you do 1 divided by that number, you should get point, and then there are 8 zeros. All right, so point 0, 0, 0, 0, 0, 0, 0, 0, 3, 4, 2. Or if you write it in scientific notation, because it is such a teeny tiny number, it would be 3.42 times 10 to the negative 9. Okay, so I think as with any lottery or lotto or whatever, yeah, somebody is going to win, but the chances that you are going to win are very, very small, obviously. Okay. All right, let's go on to the next page. And this just basically shows kind of a flowchart that I've put together over many years, having taught this counting material, to try to help you to figure out which counting method is appropriate. Okay, and there are some key questions, like right off the bat. Are you selecting with or without replacement? Okay, because right off the bat, when you decide what you're picking, if you're doing with or without replacement, that will decide which way you go on the flowchart. If you are picking with replacement, or in other words, you're just kind of doing sequential selections from different categories, then you will use the multiplication rule. If you are choosing without replacement, okay, in other words, you've just got a big bag of stuff and you're picking things out. So then the next question is, how many total items and how many of them are you picking? All right. And then extremely key is the order important, yes or not? Are you creating a specific order, or are you just creating a group of items? Okay. So if you are actually creating a specific order, then the next question is, are all your items distinct? If they are not, and we went over, a couple examples of this, then you have to use this special rule. Like, for example, when we did A, B, C, C. Okay, not all of these items are distinct, so we had to use a special rule. If all of the items are distinct, yes, then you can either do permutations, okay? In other words, NPR, and that is what I would normally do, or the multiplication rule also applies. It's basically equivalent, all right? Back to the combinations, when the order does not matter, you're just making a group, then you use combinations, in other words, NCR, okay? And then the only special case there is if you are selecting from 2 or more different subgroups. For example, like, the example we just did with the eggs, where we had a group of a dozen eggs, 3 of them were cracked, the rest of them were not. So, if you have that particular case, then you additionally have to apply the multiplication rule. All right. Okay, so let's just run through a few examples on the next page. Example 1. You've got a committee of 8 people. How many ways can we choose a subcommittee of 2 people? So first of all, we're asking with or without replacement. Well, clearly, you want 2 different people. If you pick the first person, you're going to leave them out because you're not going to pick them again because you want 2 different people. So clearly this is without replacement. Does the order matter? No, because I'm just trying to create a subcommittee, a group of 2 people, all right? So it doesn't matter what order I pick them in. So what this tells me is that I need to do a combination, and I've got 8 total people to choose from, and out of them, I want to select 2. All right? So go ahead, do that on your calculator, pause. You should find that it equals 28. All right, so very similar question. Committee of 8 people, how many ways can we choose a chairperson and a vice chair? All right, with or without replacement? Again, without, because clearly we need 2 different people to fill these positions. Does the order matter? In this case, yes, okay? Because I'm picking 2 people to be the chair and the vice chair. So for example, it's different. If I picked, for example, Paul to be the chair and Tori to be the vice chair, that is different than if I picked Tori to be the chair and Paul to be the vice chair. 2 different things. So yes, the order matters, which means we have to do a permutation. And again, the total number of objects, in this case people, is 8, and we are choosing 2 of them. Okay. And again, pause if you want to try it on your calculator, but you should find that that is equal to 56. And finally, how many 5-card hands can be dealt from a deck of 52 cards? So first of all, is it with or without replacement? Well, you're dealing out 5 different cards, so obviously it is without replacement. You're going to get 5 different cards. There's no chance that you're going to get 2 Ace of Diamonds, right? Does the order matter? No. All right, because they're just dealing you cards. And then you can pick them up and sort them into whatever order you want in your hand. All right, so because the order does not matter, that implies it's just a combination. We're just making a group. And in this case, we're selecting out of a total of 52 objects, and we are selecting 5 of them. So the combination of 52, 5, go ahead and calculate it. Pause if you want. Okay, 2,598,000 960. All right. All right, so the last 2 pages of the handouts consist of problems. Normally, we would do these in class. I want you guys to attempt these on your own. I totally get it's not as easy to do it on your own. You don't have people to talk with. You don't have me to consult. Give them a try. Okay, this is the best way to practice. Give them a try. And like I said, I'm going to look at the weather report again and see what I think is going to happen tomorrow. I may have an additional assignment for you to do before tomorrow or by tomorrow. So I will just keep that in mind. But assuming we're going to have class tomorrow, go ahead and try these problems. All right. Hopefully see you tomorrow.